All scalars, vectors, and covectors are examples of tensors. And indeed, you can build up your concept of tensors from covectors and vectors. And so we're going to look a little bit closer at covectors now. We know we can make a covector from a vector using the metric. And in Cartesian coordinates, this metric is just 1 for the 0, 0th component, and -1 for the 1, 1, 2, 2, and 3, 3 components, and 0 for all the others. Note that we're using the Einstein summation notation, where we're summing over one down index and one up index. And we have to have the free indices equal on both sides as well. So this is a covector, so it's got a one index down, and so this whole thing has to have one index down, and you see it does. It's got one left there. This is a process for getting a vector and turning it into a covector. There's an equivalent reverse process, of course, where we have some other object which is strongly related to the metric, which brings us from our covectors back up to our vector. And again, we have this free index lambda, which is in the sort of vector slot in both sides, and we're summing over one index which is up and one index which is down. Now these two things must be related, because if you can go from a vector to a covector and then from a covector to a vector, then we can string those two things together. So if I plug this into here, then remember we've got two sums, we've got two new sums and two alpha sums, but these are just numbers being multiplied together, so I can change my brackets as I like. And indeed, I've got to get my a terms back again, so this must be a delta function, because by definition, these covector terms must equal these covector terms. Once you sum over the delta function, you just end up with the same term back again. However, because this is true for all a, in fact, we need this to be true all the time. So in fact, we have that this metric summed over these metric terms has got to give us the delta function. In other words, this is just the inverse of that. That's really obvious for the coordinates we've been using, because for special relativity in Cartesian coordinates, this is just 1, -1, -1, -1, with zeros off the diagonals. And so all we're doing is we're putting a minus sign on our spacelike terms. In order to go back, of course, we just put another minus sign on our spacelike terms. So these are in fact the same thing and their own inverse. But in fact, in general, when you have non-Cartesian coordinates, or in general relativity where you have a slightly different metric, you can have rather complicated things in here, but they're always each other's inverse. The metric, by the way, was in fact our first example of a rank 2 tensor in special relativity. So this is a rank 2 tensor. You can tell that because it's got two indices. But we're going to try and talk about general tensors now. We could approach that several ways. The very mathematical way would be to describe all tensors as linear maps on vector spaces. That's a little bit abstract, but in fact, if you think about it, that's exactly how covectors are defined. If I talk about a vector and I want to describe a covector, it's the general linear map that maps that to a number. And indeed, covectors in quantum mechanics are just things that mapped vectors to a number. And indeed, again, in special relativity, we have covectors mapping vectors to a number. And so you could define them that way if you wanted. But you can see that they construct their own vector space. It's the dual space of our original vector space. And so we could describe it that way. And in fact, tensors are linear maps from vectors or other tensors into other tensors. And so it's kind of recursive. For example, here we have a metric mapping our vectors to our covectors, or a different form of our metric mapping covectors up to vectors. We met that kind of thing in classical mechanics, where we had things like moment of inertia mapping angular velocities to energy. So we had moment of inertia mapping a couple of velocities to an energy, or polarizability mapping an electric field into a polarization, for example. But in fact, we're going to talk about tensors in terms of tensor products. In other words, we're going to talk about tensors as being a vector space constructed out of a tensor product of strings of covectors and vectors. Now, what's a tensor product? Tensor product is something that we've been using for a while. If you have more than one spatial dimension in quantum mechanics, so if I have one spatial dimension which has an index x, so this is a complete set of basis states for a single dimensional wave function. And supposing I have another spatial dimension, and I have a complete basis set of states for that, then in fact, to talk about the Hilbert space of the combined system, I have to have all possible pairs of basis states in x and y, which we would have just described as a state with two indices inside it like that, but that really means the tensor product between those two. So those two things are equivalent. Another thing that we used a lot was we used operators. And an operator looks like a ket and a bra. And this bra acting on a ket gives us a number, and so we end up with a ket. So this is something that maps us from an element of the Hilbert space back to another element of that Hilbert space. And indeed, this is the tensor product of a ket and a bra. It's kind of a string of them in a particular order. In classical mechanics, when we were talking about polarizability, we had to get from an electric field to a polarization. And so the object there was the electric field covector, tensor product with a polarization vector. So this acting on an electric field gives us a number, and then we end up with a polarization. And so we've had a few of them appear. Ultimately, all they are strings of vectors and covectors. And those strings of vectors and covectors form elements of a vector space. And as with any vector space, all you really need to know to describe it fully is to describe its set of basis vectors. And so if I build a vector space, a tensor product vector space, out of n vectors and m covectors, then my basis vectors look like this. Okay, so that doesn't seem like I've defined it very well, but in fact that tells us everything we need to know. We have strings like this and strings like that. If that's a basis, then a completely general tensor is going to be a linear superposition of those objects. So you can see that we've got all our vector indices described at the top and our covector indices described in the bottom as usual, which is why the vectors had the index down and the covectors had the index up, so that our coefficients obey our normal rules. And so this set of coefficients essentially describes our tensor in exactly the same way as, for example, a position vector in 3 space. We would actually have to describe it as x times I plus y times j plus z times k. But we'd often write that just as the coefficients, x, y, and z. And so these are the I, j's, and k's equivalent, and these are the x, y's, and z's equivalent, except we have lots of different dimensions. So instead of just being one-dimensional, this is n plus m dimensional.